So picture this. It's 2022, and researchers are testing this massive, incredibly expensive new AI model on what seems like a completely basic task, just, three-digit addition.
Right, something a kid could do.
Exactly. And for months of training, as literally millions of dollars of computing power are just poured into the system, the model fails. It's essentially scoring a 0.
Just outputting garbage,
Yeah,
basically.
right. Just couldn't do it.
Yeah.
But then, and this is the crazy part, the model crosses this invisible, specific threshold of scale. Like, they didn't add any new instructions. They didn't change the underlying architecture at all.
Right.
But its success rate on three-digit addition suddenly rockets from 0 to basically 100% overnight. It just knew how to do it.
Yeah, it's the kind of behavior that makes even seasoned computer scientists just sit back in their chairs and stare at the screen. Because you're feeding a system mountains of data, and your only prompt is to ask it to predict the next word. And then suddenly it spontaneously develops a capability that literally no one explicitly programmed into it.
I mean, honestly, it feels spooky when you're sitting there using these tools and they pull a highly specific, complex insight out of what seems like thin air. It feels like magic.
It really does.
But, calling it magic is a bit of a cop-out for us. So today's deep dive is taking us right into the engine room. We want to figure out what is actually happening when you see that kind of jump.
Yeah, we're getting into the mechanics of it.
Right. And we are looking at this brilliantly detailed essay. It's by Aaron Rose from the June 1st, 2026 issue of Tech Reader magazine. It's titled, How ChatGPT Was Built, Part 4, The Math Behind the Magic.
It's a fantastic synthesis of the current research.
It really is. Our mission for this deep dive is to completely demystify that spooky behavior you've been seeing. We're going to unpack the structural mathematics that actually explain it. So, okay, let's unpack this, starting with the fact that Aaron Rose makes it very clear right up front that there isn't actually a single grand unified theory of AI yet.
No, definitely not.
Like, we don't have one master equation that just explains consciousness or intelligence for machines.
We don't. But what researchers have managed to do over the last few years is piece together a really highly robust structural account of this emergent behavior.
Right.
By borrowing concepts from all over the place, like statistical physics, information theory, and even high-dimensional geometry, they have actually mapped the mechanics of what is happening inside these black boxes.
Which is wild to think about.
It is. And it turns out the actual explanation for a machine suddenly learning to code or, do math overnight is vastly more illuminating than just waving our hands and calling it a mystery.
Okay, so I want to get to those sudden overnight jumps because that's the flashy part. But logically, before we can understand why an AI suddenly leaps forward, we have to look at the baseline, right? Like what happens when you just take a neural network and make it bigger?
Exactly. You have to start with the scaling.
Yeah. So back in 2020, Jared Kaplan and a team at OpenAI published this paper that essentially mapped out the trajectory for the entire AI industry.
The scaling laws paper, yeah.
Right. They looked at the relationship between the size of a model, its parameter count, and its overall error rate.
And that paper is essentially a foundational text at this point, because what it proved was that the relationship between size and performance wasn't just some messy, unpredictable scatter plot.
It wasn't random.
Exactly. It followed a very clean mathematical pattern known as a power law. And, power laws are ubiquitous in nature. They describe things like the magnitudes of earthquakes or the distribution of wealth, or even the sizes of craters on the moon. So Kaplan's team defined what we now call the neural scaling law, which basically says that performance scales mathematically with size.
Right, and we obviously aren't going to read out the literal equations here because that would be terrible audio.
Right, don't.
But the core relationship is stunningly simple. The math shows that every time you multiply the computing power and the model size by a specific factor, the model's error rate drops by a predictable fraction.
Predictable being the key word there.
Right. It's this reliable downward curve.
All right.
So what does this all mean? To me, it sounds like this single discovery turned AI development from a wild casino gamble into something more like aerospace engineering.
I think that is a very apt way to look at it, yeah.
Because before this, training a massive model was basically like building a bigger rocket, lighting the fuse, and just praying it reached orbit.
You had no idea if it would actually work until it was done.
Exactly. You're spending millions of dollars on compute clusters, and you just have to hope the final product is smart enough to justify the cost. But with the reliable scaling law, you could suddenly calculate the exact fuel needed, right?
Precisely. You could forecast the performance of a trillion-parameter model before you even spent a single dime to train it.
Which is just incredible.
You're touching on the core historical shift here, really, because OpenAI had the conviction to keep scaling up their models precisely because they were engineering against this known predictable curve.
They saw the math and trusted it.
Yeah. While much of the research community at the time was writing papers arguing that large language models would inevitably hit a wall of diminishing returns, the researchers looking at the scaling laws knew mathematically that the models would just keep getting better.
But hold on, I actually need to stop you there.
Yeah.
Because if the power law says improvement should be predictable, smooth, and continuous, how does that explain our model suddenly learning 3-digit addition overnight? Because a smooth curve getting slightly better at predicting text, that doesn't explain a sudden vertical jump in a specific complex capability. The smooth curve doesn't explain the magic.
And that is exactly where the Kaplan paper gets really fascinating. Because if you look closely at those scaling graphs, the curves aren't entirely perfect.
What do you mean?
Well, at certain thresholds of scale, the trajectory actually shifts. You see these distinct kinks in the graph.
Kinks in a smooth curve.
Yes, exactly. And those kinks are the very first mathematical fingerprint of emergence.
Oh, wow.
Yeah. When you see a kink in a scaling curve, it indicates that the fundamental rate of improvement has changed character. The model has crossed into a qualitatively different regime of learning.
Okay, so the power law breaks down a bit.
Right. The power law alone can't explain what happens at those specific thresholds, which is why researchers had to look outside of standard computer science for answers.
And according to the essay, they looked to statistical physics, specifically the mathematics of phase transitions. Because if you think about it, nature is full of sudden qualitative jumps. Like water is predictably liquid as you cool it down, degree by degree, until suddenly, at 0 Celsius, it abruptly locks into a solid crystal lattice.
Right. It becomes ice.
Yeah. Or, a piece of iron acting as a magnet. If you heat it up, it remains magnetic until it hits a specific thermal threshold, and then it just instantly loses its magnetization.
Exactly. And in statistical physics, that phenomenon is tracked using something called an order parameter.
An order parameter.
Yeah, it basically measures the degree of macroscopic organization in a system. So below a critical temperature, the atomic spins in a magnet are aligned, and the magnetization is high.
Okay, making sense.
But as you add heat, you're adding thermal noise. And above a certain critical temperature, that thermal noise just completely overwhelms the alignment.
So it just breaks down.
Right. The magnetization doesn't just slowly fade away, it drops precipitously to 0. And the mathematics of that transition is expressed as a threshold function.
Got it. And the essay maps this exact threshold function onto large language models.
Yes, beautifully.
The capability, whether it's 3-digit addition or, translating Persian poetry or writing a Python script, is mathematically 0 below a certain critical scale.
It physically cannot do it.
Right. But the moment the model crosses that critical threshold of parameters in compute, the capability is suddenly greater than 0. It abruptly exists.
The crucial thing to understand about that threshold function, though, is that it completely ignores the continuous improvements happening under the hood.
Wait, what does that mean?
It only measures whether the macroscopic system, the whole model, has crossed the boundary of being able to perform the task successfully.
Wait, so it's like a kid learning to read. Aaron Rose uses this analogy, and I'm just thinking about it now.
It's a great analogy.
From the outside, as a parent, it looks like it happens overnight.
Yeah.
One day, they're just staring at the picture book, making random sounds, and the next day, they're reading the sentences out loud. It looks like a discrete sudden jump.
Right, exactly.
But the child's brain didn't just spawn a fully formed reading module overnight. It was quietly building the neurological wiring, synapse by synapse, for months.
If we connect this to the bigger picture, your analogy highlights the exact mathematical reality of a neural network.
Oh, really?
Yeah. The phase transition framework implies that the physics of the system, the billions of weights and biases shifting by tiny microscopic fractions inside the AI, those are changing continuously throughout the entire training process.
So the learning is gradual.
Yes. What changes discretely is the macroscopic observable behavior. The capability only becomes measurable to us once those continuous internal changes cross the threshold of being reliably useful.
Oh, yeah.
So it is continuous underneath, but discrete on the surface.
Okay, I follow the logic there. Smooth scaling leads to underlying changes, which eventually trigger a sudden phase transition in behavior. But I'm still stuck on the why.
The why is the best part.
Right, because if the model is continuously building infrastructure under the hood, what exactly is it building? And what is forcing it to do so? Because OpenAI didn't code a learn the rules of three-digit math objective into the system. The only objective we ever hear about is just predict the next token.
To answer that, we have to lean on Claude Shannon's information theory from the late 1940s.
Okay, taking us back a bit.
Yeah. Shannon was trying to mathematically describe the fundamental limits of communication over noisy channels. Think telephone lines, radio waves, that sort of thing.
Yeah.
But if you view a large language model through the lens of Shannon's equations, you realize something really profound about its true nature. An LLM is not fundamentally a prediction machine. It is a compression machine.
Okay, I hear you, but calling it a compression machine feels like a massive leap. When I type a prompt into ChatGPT, it generates new text. It predicts the next word. How is that compression?
It's compression because of the massive scale of the training data.
Explain that.
To successfully predict the next token across the entire internet's worth of human text, the model is forced to find the most compact, efficient representation of that data possible. It physically does not have enough parameters to just memorize the internet word for word.
Oh, okay.
Right.
Here's where it gets really interesting. Let me try to visualize the constraint you're talking about.
Here for it.
It's like packing for a month-long trip across multiple climates,
Right.
from the freezing mountains to a tropical beach.
Right.
But you are only allowed to bring a tiny 15-liter backpack.
That is a very tight constraint.
Exactly. You can't just memorize your daily routine and pack 30 specific distinct outfits. The physical space of the backpack simply won't allow it.
Right.
You are mathematically forced to pack versatile layers, like a merino wool base layer that works in the snow but also breathes in the heat. Because the model physically cannot memorize the entire internet, it is forced to abandon memorization and instead learn the underlying versatile rules of language.
Yes. That tension you just described, the backpack constraint, is formalized in an equation known as the information bottleneck.
The information bottleneck.
Exactly. The model is trapped in this relentless mathematical tug of war. On one side, it is trying to minimize its prediction errors. It desperately wants to perfectly guess the next word in the training data.
Right.
But on the other side, the bottleneck forces it to minimize the amount of raw information it actually retains from that data.
Right, because if it held on to all the raw data, it would make perfectly accurate predictions on its training set, but it wouldn't generalize to a new prompt I give it.
Exactly.
It would essentially just be an incredibly expensive search engine returning exact quotes.
And conversely, if it compressed the data too aggressively, throwing away too much detail, it would lose all accuracy and just spit out gibberish.
So there's a balancing act.
A brutal one. The training process is this intense optimization game to find the perfect balance between compression and accuracy. And information theory research proves that when compression is pushed past certain critical thresholds, the internal representations of the data don't just gradually shrink.
What happens?
They undergo a discontinuous change, a phase transition.
There's that term again.
Yes, because under the pressure of the information bottleneck, the model stops representing the surface-level statistical patterns of the text, like the mere likelihood that word A follows word B.
Okay.
And it starts representing the deeper, latent structure that actually generated those patterns in the first place.
Oh, wow. It stops memorizing the symptoms and learns the disease.
Yes.
It learns the actual abstract rules.
Precisely. And this abstraction is the exact mechanism underneath the spooky behavior we talked about.
So that's the magic.
Right. When a model compresses human language hard enough, it is mathematically forced to uncover the latent structure of reality embedded in that language. And because it begins to map that structure, brand new capabilities naturally emerge, because the capabilities are already implicit in the underlying logic of the world.
Okay, I have to push back here for a second, because latent structure and abstraction still sound incredibly philosophical to me.
That's fair.
We are talking about silicon chips and code.
Yeah.
If we are saying the machine has built this deep understanding of reality because of compression, what does that actually look like if we peek inside its brain? Show me the physical structure of understanding.
Okay, to see the structure of understanding, we have to look at the geometry of the model's internal brain.
Geometry, okay.
When a large language model processes text, it doesn't read words. It converts tokens into vectors. And a vector, in this context, is just a long list of numbers.
Just data points.
Right. But mathematically, those numbers represent coordinates in a vast high-dimensional space. We call this the latent space or the embedding space.
And when you say high dimensional, you don't mean 3D space like a room. You mean thousands of dimensions.
Thousands, sometimes tens of thousands of dimensions.
Which is mind-bending.
It is entirely impossible for the human brain to visualize perfectly. But the geometry of that space, literally how these vectors are arranged, how they're clustered and distanced from one another, that encodes everything the model knows. Distance in that space equates to semantic similarity.
The essay actually gives a really concrete example of this.
The text messaging one.
Yeah. If a model has learned to distinguish between, say, formal academic text and informal text messages, it will have vectors for formal words that are physically clustered together. And they'll be separated by a measurable distance from the cluster of informal words.
Exactly.
But if the model hasn't learned that difference yet, all those word vectors are just jumbled and mixed together in a chaotic cloud.
What's fascinating here is that this geometric arrangement gives us a precise, measurable condition for when an emergent capability has actually occurred.
Oh, really? There's a metric for it.
Yes. It is called the geometric separability condition. For a model to reliably perform a task, the representations relevant to that task must be linearly separable in the latent space.
Linearly separable, meaning you can draw a straight line, or I guess a flat plane, if we were in high dimensions, straight through the data to cleanly divide it.
Exactly.
So what does this all mean? It means the magic is just topology. Let me try to conceptualize this one.
Let's hear it.
It's like having a wildly messy two-car garage.
I know that feeling.
Right. For months, it's just a chaotic, intertwined pile of cardboard boxes, bicycles, and power tools. But over time, you slowly start shifting things around. You move a wrench here, you slide a helmet there.
Just reorganizing.
Yeah. And then one day, the garage gets organized to the exact point where you can walk in and draw a single clean chalk line right down the middle of the concrete floor. Tools strictly on the left side, sports gear strictly on the right side.
That's a perfect image.
The moment that straight chalk line is drawable, the capability of instantly finding your hammer emerges.
And the math actually backs you up there completely. The linear separability equation essentially dictates that there must exist a direction in the model's internal space that correctly classifies all the inputs relevant to a capability.
A clear path.
Right. Before emergence, that boundary cannot be drawn. The vectors are scattered like your messy garage. But as models scale up, their latent spaces undergo real topological changes.
Wait, what does a topological change or manifold smoothing out actually mean in plain English? Because the essay drops those terms and it gets a bit dense right there.
Okay, think of a manifold as a crumpled piece of paper floating in a room.
Okay.
The data is written on the paper. But because the paper is wadded up into a ball, points that are actually far apart on the sheet might be touching each other in 3D space.
Right, they're folded onto each other.
Exactly. As the model trains and compresses information, it essentially irons out that crumpled paper. It smooths the manifold. It disentangles the raw data into a clean, structured geometry.
It flattens it out.
Yes. Clusters merge together, the crumpled shapes flatten out, and suddenly you can draw a straight line between concepts that were previously hopelessly tangled.
So every time the geometry shifts and smooths out like that, a new chalk line can be drawn, and a completely new capability becomes accessible to the user.
Precisely.
That is wild. When researchers were watching early models suddenly ace benchmark logic tests that they were never explicitly trained for, they were actually just witnessing the model's internal geometry reorganizing itself enough to support a new separating boundary.
It's not magic. It's high-dimensional geometry.
Unbelievable.
So, if we look back at the whole picture we've built, scaling laws dictate the predictable growth of the system. Phase transitions define why the capability leaps appear sudden on the surface.
Right.
The information bottleneck is the pressure that forces the model to learn deep structural rules rather than just memorizing data. And representation geometry is what that deep structure physically looks like inside the machine.
It is a highly coherent, interlocking structural account.
It really is.
It is incredibly coherent.
Mm.
But we do have to be intellectually honest here. And Aaron Rose emphasizes this heavily toward the end of his essay.
Yes, he does.
We have this beautiful structural account, but that does not mean we have the whole phenomena entirely figured out.
No, not at all.
Having the equations for geometry and phase transitions does not mean we possess a grand unified theory from first principles.
We certainly don't. The math gives us the how, but it still struggles with prediction.
Meaning we don't know what comes next.
Right. We cannot yet mathematically forecast exactly when a specific brand new capability will emerge. We don't know why some logical abilities require a trillion parameters, while others show up surprisingly early in a model's life cycle.
It's still a bit of a guessing game in that regard.
It is. And there are massive mysteries left entirely unsolved. We don't have an equation that perfectly explains why chain of thought asking the AI to think step by step boosts performance so dramatically.
Wow, that's still just a behavioral trick we found.
Exactly. We don't fully grasp how models manage to learn entirely new things in context during a conversation without actually changing any of their underlying geometric weights.
Realizing how much is still unknown actually deepens my appreciation for the original engineers who built these systems.
How so?
Because they didn't have all this topology and bottleneck math perfectly sorted out before they launched the first massive models. They built the system first.
They absolutely did.
They based it on an intuition and a conviction about the scaling laws of the transformer architecture.
Yeah.
The advanced math we just spent the last, 15 minutes talking about, that came later.
It was retroactive.
Exactly. It came as researchers desperately tried to explain what the engineers had already unleashed.
This raises an important question about the current era of artificial intelligence. We are living through an unprecedented race between our engineering achievements and our theoretical understanding of those achievements.
Usually the other way around, right?
Usually, yes. Historically, theory often precedes invention. You understand the physics of aerodynamics and then you build the wing.
Right.
Here, the build came first. The build changed the world. And now, the theoretical physicists, the information theorists, and the mathematicians are sprinting to catch up, desperately trying to measure the topological chalk lines inside a machine that already exists.
It is a wild time to be watching this field unfold. So, to bring this all together for you listening, the next time you use an AI tool and it does something surprisingly clever, or it connects two ideas you never would have thought to connect,
Yeah.
I want you to banish the idea of a ghost in the machine.
No ghosts, just math.
Exactly. Don't picture a mysterious spark of magic or a consciousness waking up in a server farm. Picture the math. Picture an information bottleneck aggressively squeezing massive amounts of data, forcing the machine to abandon memorization and abstract the underlying rules of reality.
Beautifully said.
Picture that compression carving out brand new geometric boundaries in a 10,000-dimensional space.
It is deeply humbling, honestly, to realize that the deepest nuances of human language, the structural rules of our logic, and the vast web of our collective knowledge can be mapped, organized, and navigated entirely by topology and compression algorithms.
It really is humbling. And it leaves me with one final thought to mull over, a thread the essay hints at which I haven't been able to stop thinking about.
Oh, what's that?
Well, if a machine's sudden, unexplained spark of genius is really just a macroscopic phase transition driven by the relentless mathematical pressures of compression and geometric sorting, does that imply that human intuition might be exactly the same thing?
That is a deep question.
Right. When you have a sudden aha moment or a brilliant creative insight out of nowhere, are those just biological phase transitions happening in the neural networks of your own brain?
It makes you wonder.
Are human sparks of genius just waiting for their own topological equations to be discovered? Something to think about the next time you have a great idea.